on life life cycle analysis. Um, and it was a very interesting project funded by USDA. It was basically a life cycle analysis for a new domestic source of natural rubber in the Southwest in the US. And we wanted to see what is the environmental sustainability. There's a water consumption, environmental impacts, global warming, and all of that for that new source of rubber. It was very interesting. Uh, but later on, I found out about Klaus, and I contacted him and tried to join his team on air capture. And my master's experience really got me interested in this holistic view of technologies. And although my background is in chemical engineering, I'm really interested. It made me really interested in this like bigger picture questions that you can ask about technologies. And I was lucky enough that Klaus is so amazing, and he gave me the freedom to choose what I want to do as a PhD. And I worked on basically very bigger picture questions for direct air capture. One part of it was I worked on a sorbent material for DACC, which is a huge like field of research, and there's just so many different sorbents coming out every year. We wanted to ask the question that what makes a good sorbent, and we basically did a very an analytic modeling to see what are the important factors in the economy of sorbent that sorbent developers need to be concerned about. Um, and it turned out that they need to make really robust sorbent because the longevity of the sorbents that we currently have, they are not even as close as what they have to be. They need to last for tens of thousands of cycles, if not 100,000, to be economical, given the CO2 prices that we assumed in the model. That was one part of my project. The other part was I focused on the role of DAC in the existing infrastructure, mainly focused on natural gas power plants. We wanted to see if we want to use two technologies. One is the classical post-combustion capture, which is basically a tailpipe capture. You put it at the power plant. You have to retrofit it significantly to capture the CO2 versus if you indirectly capture it from air by your DAC. Which one becomes cheaper if you look at every single power plant, natural gas power plant in the US? And it turns out even at a high cost for DAC, like $500 per ton, it would be still cheaper for one third of our natural gas emission to be captured by DAC compared to the point source capture, like post combustion capture, because it's very expensive first for post combustion capture. And also, it makes you to make a significant change in the power plant. And if your power plant is not running all that often, which is the case a lot of times for natural gas power plants, then you are making a huge investment that is just sitting there and it's not running. So that makes your carbon very expensive. That's why DAC is very special in that sense. So that was another project. And then I continued. And as a part of that, I worked on also in this paper that you just mentioned that we recently were successful to publish it, which was basically looking at how much external support is necessary for DAC to make it economical, to make lower the cost to a threshold that is ideal and everybody talks about, which is $100 per ton. We basically wanted to see how much you have to support the technology to be self-sufficient eventually, basically. And if you're interested, I prepared a presentation, just go over more details about that paper.
Yeah, I was going to ask you if you wanted to just, however you want to do it, just a high level overview of the paper and its main sort of arguments and findings. That would be great. Actually, I'd love that. And let me also want to Habib, consider this just sort of a welcoming for you. You know, you have a broad range of expertise here. You know, we have some people from our R&D team. I'm glad that Dal was able to make it. Dal Winters, who's embarking on a sort of a sorbent mission for us. We want sorbent making in group research a big part of what we do openly. So everything you just said there, I'm sure Dal and some of the folks on the R&D team would love to pick your brain on what makes a good sorbent. So, but consider yourself very much welcomed into the community and really great to have you.
Thank you. Appreciate it.
So let me go ahead and let you share your screen. One second. Just going to give you permissions there. It should work now.
Okay, I'm going to share my second screen.
What I might do, Habib, because the folks on the call, myself, it's a wide range of people with different backgrounds. So I might pause if there's an acronym or something like that to just have you elaborate a little bit, if that's okay.
No, that's actually what I thought. So it's pretty I try to not make it like very just very focused on a specific audience who are familiar with DACC. It's definitely, but please feel free to interrupt me and ask questions whenever you want to. So, yeah. So basically the idea was looking at learning curves and learning by doing, which is an empirical phenomenon that we have been observed in many technologies. And what it basically says is that as you keep building more of a specific technology, especially a new technology, your cost tends to come down. And there is a correlation between your cost reduction and the total number, cumulative number of units or capacity of that technology that you build. And this has been observed in many different technologies, from solar PV, which is very famous for that, to car engine, like internal combustion engines, to fuel cells, to electric cars, everything, a lot of technologies basically. And it's not as specific to solar, because a lot of people mention like, why do you compare air capture with solar? But this is just an example. It has been observed in many different technologies. And it basically, the way it works is that we say roughly for every doubling in number of units that you produce, you will have a certain percentage of your cost goes down. And that's your learning rate, what we call it. For example, if you have 2 units, if you make it 4, your cost goes down from $100 to $80. You will have a 20% learning rate, for example. If you make it 8, another 20%. If you make it 16, another 20%. That's how it works basically. So it has a power function relationship. And you can see, I'm not going to just go over a lot of equation because the paper is really equation intensive. But this one, you can see, if this is the cost of nth unit, it's a function of the cost of first unit times the log of 2 of n is basically the number of doublings, because you're counting how many times you're doubling. And epsilon is basically like, if your learning rate is 20%, epsilon is 1 minus learning rate. It's basically you times your cost, your initial cost to the what we call progress ratio. For example, this is 0.8 and you have 1 doubling, your initial cost goes like 80%, will be the 80%. Your cost of nth unit will be 80% of your first unit, and so on. So that's basically what it is. It's very simple. And one problem with that is it's pretty much like a black box. For example, if you look at solar, this is the cost for solar. So it's 1975 to 2018. You can see in 1975, it was about $120. And here it came down to 38 cents per watt, basically. It's massive cost reduction. And you can see the capacity went from roughly 2 megawatt of produced solar and installed solar to, this is about 500,000, 500,000 megawatt in 2018. And you can perfectly see, for example, here you can see in 2018, in 2008, it seems like the cost was almost flattening, but again, we had some sort of breakthrough, which I believe, I'm not quite sure, but I believe it was because of like something related to silicon sources. So they found out to just, use another, I'm sure you know better than me.
Yeah, that was the year where I believe solar PV was always standing behind the semiconductor. It was sort of a second taker on access to silicon. And that was where it started to get market share, where it was able to jump ahead in the line. And that might also be when the real commercial PPA market really kind of took off as well.
I see.
What was happening around then.
Interesting. Yeah. So, but the problem is this equation is just a black box. It doesn't tell you why. It just tells you, it happens. If you keep building more, it will eventually get cheaper. So, and one important consideration here is that it's typically not recommended to use this for projecting, for basically predicting future costs. They say don't use it because there are a lot of uncertainties, especially in a case that you have two new technologies and you want to say, okay, which one I want to do investment, which one is more promising, then let me just put both of them on a learning curve and see which one goes down. They say you shouldn't do that. That's not the right way of using it. So what we did, we just wanted to get a ballpark of how much learning we need for DACC to get the cost down. And here you can see the orange curve with uncertainty areas around it. That's the shading, basically the shaded area around it. You can see the cost had to come down from 1975 to 2011. It came down almost 100-fold. And basically it got cheaper for 100 times. But how is the situation for DACC? In 2019, it was a New York Times article that is stated from Climeworks that they are between $500 to $600 per ton. So if we get that only 10 folds cheaper to get to $50 to $60 per ton, that would be fantastic. That's basically what we need. So we have a much easier job. And if you go with the same slope that you can see for solar here, for DACC, you have the same slope of getting 10 times cheaper. You only need to go from a kiloton level that we are right now to a megaton, only 1,000-fold increase in the capacity, versus for solar, it was like 50,000-fold to get 100 times cheaper. So
can I ask you a quick question on that?
Yeah.
So I think one of the things that solar is interesting is that it very early on, there was a dominant design where it was silicon-based modules and cells that were produced more or less in the same way. There was some variation. So when you're talking about DACC, does it matter when you essentially have liquid sorbent type of carbon air engineering technologies versus the climate? They're totally different. They might do the same things, but do they really relate to each other? Like, do you have to look at those as almost two separate technologies that have their own learning curves?
Yes, I'll explain that in a little bit. And that's a very good question. Definitely, that's something we thought about. But I'll definitely explain, especially for the comparison that you made between carbon engineering and Climeworks. I'm going to talk about it. So this was just basically, we wanted to see how difficult the job is, and it turned out it's pretty easy for DACC compared to solar. And we basically looked at. This is just a little bit of details about modeling. We had to make an assumption because for learning curves, if you continue to going down, you'll get to zero, which is impossible, like technically. So that's one of the issues with learning curves, that you need to have a cost floor to say, okay, I cannot get cheaper than this. And that was exactly the same assumption that we made here. So we say the cost of DACC has two components. One component is the reducible cost, the cost that can be subjected to learning, and the other component is the residual, which you will not be learning for that. That's basically the minimum, let's say, thermodynamic amount of energy that you need, or the minimum amount of material that you would need, you cannot get cheaper than that. And that's your ideal cost in the future. If you ever get super cheap, this will be your cost. But the first is all the inefficiency that you can take care of it and you can make it cheaper. So for the nth unit, if you produce so many, the nth unit it has a CN, which it has a relationship according to learning curve with C1, your initial cost, and your residual cost, which doesn't decrease. It's still the same. So that's how we basically built our model on top of this simple assumption. Which makes the model like a little bit more realistic. And the other point was that, as you know, there's a lot of like uncertainty, and these companies don't really publish the cost. So we wanted to make simple. We didn't want to focus on any specific DACC design. We just wanted to go very general. This is just the technology. But obviously in our learning model, we will have more assumptions that I'm going to talk about. So what the model does is that this is basically these curves. This one and the previous one for solar that I showed you, these are log axis because you have a power function. So that's why you see a straight line. But if you put it on a normal axis, it will be a curve like this. So the red curve is basically the cost of DACC. You can see the first couple of units are very expensive, and you have a very sharp reduction at the beginning when you start building more units because you have more doublings. For example, it's easier to go from 2 to 4 to 8 compared to if you have 100 units, you have to make another 100 to have one more factor of learning. So the cost reduction at the beginning is very steep, and then it slows down the road. And we assumed this is our residual cost, which in the future you will reach, this red curve will reach the residual cost if you make so many units. And basically you have a target cost. This was the main assumption, that there is a cost that it should not be as low as residual cost, but for the purpose of climate change, that's what we want to look at. That's a threshold. Basically, if you make that as cheap as the target cost, it will just be self-sufficient and you wouldn't need external support. The technology, the markets will be open for the technologies, and it will just continue its learning path without any external support. But what is that external support that you initially need is here. Before reaching the target cost, this is the number of units that you reach the target cost. This is how many you need to build, basically, the cumulative numbers. And when you reach that, then you're lower than your target cost. But before that, anything extra will be your, that's the number of units. Anything extra will be your excess cost. That's the excess cost that you would need external support, either in form of investment from a company or in form of a government subsidy or whatever you want to think about it. But that's what needs to be invested in DACC. And obviously for the first ton, for the first unit that you're capturing, you're only selling it at the target cost. So the difference is huge. You have to pay a lot of excess. But as you're getting cheaper, your excess cost goes down until it eventually goes to zero at this point. So that's basically everything, that all these parameters that the model calculates. And the whole area, this shaded area and this hashed area together, that's your total cost for reducing. But you only have to find funding, external funding for the excess cost portion of it, because the rest of it, we are assuming there are niche markets that you can sell it at the target cost. There's a market for that. So here are some assumptions that in the model, that it comes down to the question that you asked, Chris. And the main part is the learning rate. Like you said, these are very different technologies. How do you compare them? And this was our main assumption, that if you want your DACC to have a very steep cost reduction, similar to solar, you would have to go with the small modular units, similar to what Climeworks is doing. And there are several reasons for that. First, generally, if you look at the body of literature, the small modular units tend to have a higher learning rate. And there are a couple of reasons that they say for that. One is, if you have a small modular unit, you tend to build more. Like compare Climeworks and Carbon Engineering right now. Carbon Engineering built one initial plant, was for demonstration. Now building 1 million ton unit, that is only their second plant. But if you look at Climeworks, they already built some, they make basically small modular units. They build just, I don't know how many of them for their Switzerland plants. Now they're building more for the projects in Iceland, and then more after that. So the number of units that you build is much more versus just the 2 units that Carbon Engineering has built. So you will have more doubling. That's why your cost goes down faster. It's one important assumption. The other one is that if you compare these two again, the lifetime of the plants. Climeworks is building a small plants that they expect only 10 years, or we recommend even shorter, 5 years lifetime. But Carbon Engineering is investing in a 20-year project. And when you build such a huge investment, you barely want to touch it, want to make any tweaks to make it better. And that has been observed in power plants, in many different technologies. But Climeworks, they always have a new generation coming up. They always want to, because they're just a small units, they don't care. It's not a huge investment. They just say, okay, for the next one that we're building, we're going to make these changes. And it's pretty easy to make changes. It is true that at the beginning, you start more expensive because you're not taking advantage of the economy of a scale. Carbon Engineering, they're making huge plan and take advantage of the economy of a scale. But for Climeworks, they start more expensive, but they have a steeper learning curve. And I can send you, it was actually a previous student of Klaus that he basically, his dissertation was only focused on this small modular technologies and why we always observe them to have a higher learning rates.
Please.
And
Yeah, definitely. There's a couple people.
does that answer your question?
It does, but this is a fixation of our community, and there's particularly Lucia and Naeem who are on the call as well. We're writing a paper where that's really at the core of our argument. Everything you just said is sort of music to our ears from an affirmation point of view, but that paper that you just referenced, if you could send that, post it, you'd have a good audience here. Habib, can I ask a question? Since everything you're saying is fascinating, we're technically at 7 minutes left.
Oh,
would it be okay for us to tack on? And I know some people are gonna have to jump. Could we push this another 15 minutes longer, or do you have to jump off at the half hour?
No, I am available. Yeah.
Okay, and then we can obviously keep asking you questions on Discord.
Yeah, I can definitely stay longer, and I can go faster if you want. Sorry, I lost track of time, but yeah, that was the main assumption. We assume basically like an epsilon of 0.79 is 21% learning rate, which is low, still lower than solar. There are some technologies you see up to 30%, but we kind of assume that, as you can see, this is the size of our unit. We are looking at only 1,000 ton per year units, very small with a short lifetime, 5-year lifetime. That's what we're looking at. So we had the assumption of a small modular for sure to use a high learning rate. And this is the cost. Basically, this is the $500 for 70 plus 30 that Clientworks has. We assume $30 is the residual cost that is never coming down. But for the other 470, you can get cheaper. That's when you have most of your learning. And then for the target cost, we assume $100 per ton. And that basically depends. There are many sources that cite the $100 per ton for DACC. They mentioned this is a threshold. There's also, if you look at the commercial CO2 market in the US, we have multiple, globally, we consume like 200 million ton, between 200 to 250 million ton of CO2 per year. But a lot of that goes to EOR, but also there's some very specific application like for food and beverage mainly for food and beverage, that the cost goes high. And that mainly is very location specific. For example, we are in Arizona, we don't have any source of CO2 nearby. For the cost of shipping CO2 will be very high. So we might even end up paying $200 for a ton of CO2. So this $100 per ton was based on that assumption, based on a niche market that you can find. And if you put these numbers in the model, you get you get a total cost of 200 million, the whole area, until you reach the threshold cost. Excess cost, the one that you need external support, is about 50 million. The number of units will be 300 units, not 300 million. And the total captured CO2 is about 1.5 million ton, which if you compare it only in the US, we use about 4 million ton for food every year. So there's definitely market to get the price to $100 per ton. For beverage, we use around 1 million ton per year. So this basically says you don't need to do much to lower the cost to $100. That was the main assumption. That was the main basically learning from this.
Habib, can we do it entirely without EOR? That's a really important question, because we think that EOR is politically toxic in some ways. Yeah. Can we get to that 100 without using EOR at all?
If you look at the numbers in the US, yeah, like I said, 4 million for food, almost 1 million for beverage. EOR, and the thing is, it's very difficult to compete in EOR because they usually get very cheap CO2. We are assuming $100 per ton, but for food and beverage, they do pay more than EOR. So you have even a better market outside EOR. Yeah. And obviously 50 million is really low, but the whole point was that if you want to see DACC is going to work, if you want to see if you are observing learning, that's how much investment you need to make. If you pay 50 million and you don't see anything, you say, okay, DACC is not going to work. But if you pay 50 million and say, oh no, I'm kind of seeing this learning curve, then it means the technology has the promise that that everybody is talking about. And the other important learning was comparing this excess cost with other costs that, for example, the Department of Energy is making. You know, like they spend almost $1 billion for the Petronova plant, just one single plant. And they make much more annual investment in renewables, in fossil fuels even. So this is basically a peanut for them. This is nothing. And this is a one-time investment. So finally, I'm going to go through the uncertainty analysis, because all of these parameters that we talk about, there's a huge uncertainty and people say, no, this is not right. The learning curve, the learning rate could be different. The costs could be different. So we assume the large range of uncertainty for each important parameters. This is basically alpha translates to learning rates. So this translates between the 30% learning rate to 0 learning rates. Basically, if you don't have any learning rates. We gave an uncertainty range of for that range to these parameters. For the reducible cost, we assume it's between $140 to $1,600 per ton. This was the median. This was the main value that we used, but we assume the range around it. And for the residual cost, we assume $10 to $90 per ton. And we just fed all of these to the equation. It's basically like you simulate the same calculation for 10,000 times, for 100,000 times. And you see with all of these randomly distributed values in this range, what is the excess cost that you get? That's basically what Monte Carlo simulation is. And you kind of look at all the possible outcomes and then see what is in the final excess cost that you have, what percentage of the cost is below this much, or like how is the distribution of your final output. And this is basically the results. You can see the x-axis is the excess cost. This is the amount of cost that you have to pay for all of these simulation, and the y-axis shows you all the simulated models. For example, the way we read this is that if you make $100 million investment, you have a success chance of 10% to get to the target cost that you want, according in the framework of the model, in all the simulated cases that we did. If you go 100 million, you get roughly to 55-60% chance of success. And if you go roughly to 2 billion, I believe, if you make 2 billion excess cost investment, you have a 90% chance of success that you can make it to $100 per ton. And this is the same calculation for $50 per ton and for $200 per ton as the target cost. So it just gives basically accounts for all the uncertainty in different parameters in the model. And then finally, for the time trajectory, how much time does this need? Because the learning curve models, basically, they do not have a time factor in them. It's just the number of units that you produce. So you basically need to give like a growth rate for the technology to account for time, to add time to your equation. So we assume different growth rates, like 25%, 30%, 40, and 100% annually. And how long does it take to reach to that number of plants that cost goes below $100 per ton? And you can see this is the cost starting. This is for the 25%, I believe. And every year you're building 25% more plants. And this is the annual revenue, the black bar that you get from selling your CO2 at $100 at the target cost. And this is the excess cost that you have. Initially, you have a lot of excess cost, but eventually you'll catch up to your excess cost and you make more money than the subsidy that you need to get, or your excess cost. And then excess cost goes down as your plants get cheaper and cheaper below $100. So for example, for different cases, you can see like it takes 5 years or 3 years to reach this point that you make more money than your excess cost. And to reach no excess cost, like this point, this is how long it takes for each growth rates for the technology. And yeah, that's all the slides that I have.
That's great, Habib. Thank you so much. I see there's a lot of questions that some folks have asked on there. And so I think what I'll do, Habib, if you don't mind, I think I'm going to take one of our channels here, maybe what we currently call the reading group channel. Okay. And people can ask you questions there. I don't want to mob you, but I think there's probably, I myself have a ton of questions, would like your feedback on some stuff, but are you okay with that? If just over time, we could just sort of continue the conversation on the channel that way?
Definitely.
Great. So why don't we go ahead and get into some of the questions that were asked on the chat here. Let me just pull Nikhil real quick here. If you're still on, Nikhil, are you there?
Yeah. I mean, it's. I think my question was sort of answered in this. I was expecting the learning rate to change over time, but it's sort of I guess a stylized number based on like two like points in time, and then you get the learning rate from that. But just like to try and go back to that comparison with solar. I guess would the learning rate start out like low, and then as you have more and more units, it might change, or other factors? Is that, or does that not make sense?
For solar, yes, this is just one line. You can see this is the dotted line. That's the power function that we fit. But obviously, you can have different learning rates for each one of these phases. Like this can have the line of its own. This one can have another, between 1990 and 2008, another learning rate. And same here. Yeah, you can definitely assume different learning rate, especially they say as technology get more mature, your learning rate tends to go down. But that again, it just adds to your assumptions. Our main point was we want to have a simple model, because there is a lot of value in simple models that you can basically see how these different parameters interact with each other. And you can do a lot of like cool math and uncertainty analysis. But as you keep adding more assumptions like that, yes, you can definitely do that. And you need to be very realistic. First, there is a lot of uncertainty in the assumptions that you make, but also it just takes away the power of an analytic model, I believe. Then you would have to have a different learning model for every phase of the technology, and it certainly adds more complications to the model. But our main goal was to just have something simple initially, and then if you have more data or if you have some good assumptions, you can certainly add that later on. There's this paper about batteries. It's a famous Nature paper. I can send it to the group. That it does show different kind of batteries learning rate for them, and it shows as they are in different phase of their lifetime, you can see learning rate changes. But we also have a section in the paper that we talk about that too. I didn't have it in the presentation, but there's a part of paper that talks about it.
Great. Why don't we do hand raise? Naeem, I see you have your hand raised, and Sue, you had a bunch of questions too. So if you still have them, raise your hand. But Naeem, go ahead.
Thanks so much, Chris, and thanks, Habib, for this this presentation and for the paper. It's really great. I've been looking for, papers that cover kind of deployment of DACC that's not in the 1 megaton or more industrial facilities, and so this is really great. I think what would be really cool is if we can develop like an online calculator to take the kind of inputs that you have here, the range of inputs that you have here, and like change things like the useful life of a modular DACC unit, or the size of the deployment, or other kind of factors here to see how the cost would change. I think what's really, I think that would be kind of an interesting project to think about. But I think I think what's really valuable about this is that I think it's a really useful kind of North Star for people working in direct air capture in terms of like, what are we working towards in the kind of near to medium term? It's like, really, this is about millions of tons deployment of modular direct air capture to get the price down to that $100 per ton. Like that feels like something that people at OpenAir and other places that are working on direct air capture, care about scaling up direct air capture, can feel like in the next 10 years, that's something that they can start trying to work towards. So that was really valuable. I'm curious to know, like, I think a lot about modularity in terms of not just the size of the actual module and like that we have like a self-contained module of direct air, a direct air capture unit, but also modularity in terms of interoperability and the ability to bring in kind of new components as old components become obsolete, for example. So we don't have too many kind of curated interdependent parts that are then hard to kind of switch out. How is that considered in this, and how might that affect things like learning rate or like the useful life of a DACC unit, which is based on 5 years? And then secondly, real quick, is also just why was kind of 5,000 tons of CO2 captured kind of used as the basis for like what could be kind of more modular or smaller deployments of direct air capture, and not something like 500 tons? And how might that affect kind of your starting point instead of starting at $500 per ton? Like, could that be? I'd imagine it'd be much higher if we were talking about not 5,000 ton farms, but 500 ton farms, for example.
Yeah. So regarding your first question, that's a very good point, and I think it shows its importance when you talk about sorbents, because sorbents are the most important part, and that's where you need the most amount of innovation. The rest of the system is basically, we have had the technology around for a long time, and we know how to do that. We know how to compress CO2. We know about like pipelines if we need and all of that. But sorbent is the most important part, and that I think is where you need to observe most of the learning. And your question is very good. Yeah, modularity and giving the building system in a way that you can test different sorbents, I think it's a very important part, because you should expect sorbents change every year, if we not multiple times in a year, because there's a lot of innovation going, ongoing innovation, and that certainly is something you need to consider in your design. But at the same time, if you are building a plant that is not a multi-million-dollar or billion-dollar investment, then you don't mind to build another one with the new sorbent. That's the whole point. If your plant costs only a couple of $100,000, then you can certainly build more for new sorbents and have like different generations. Like if you drive from, actually it's from here, when you drive from Phoenix to Los Angeles, there's this area, Palm Beach in California. Sorry, Palm Springs, that you drive all the wind turbines under. There's huge number of wind farms there, and as you drive, you can see different generation of these wind turbines, and that's just fascinating. You can see how they keep building, but they still have the old ones, but they keep every year building a new one, and you can easily notice which ones are newer, which ones are like from the shape of the blade, from the size of the wind turbine, and that is the case here. You just have to make so many, and you have to try many sorbents to get where you want. And your point about modularity in different components is very important, but I think the most important one is sorbents, for sure.
It sounds like almost like the essence of it. It's modularity, also simplicity to a certain degree, I would imagine, has bearing on learning rates, and then kind of almost like sorbent interoperability or agnosticism seem to be kind of like three factors that could really have an influence on the learning rate. But I know Sue has a bunch, always has good questions, and has a bunch of them now, and I know we've got about 5 minutes. Sue, you want to go ahead and ask your question?
Yeah, so I'm glad you brought up wind. So I'm curious about mechanical versus electrical systems and the effective learning rate you can have, given that you're contacting air as opposed to just trying to generate electricity. And sort of along those lines as well, there's the sorbent-based solutions, but there's also the electrical based solutions like Verdox, and I forget the other one that just got an award. Do you see any differences when trying to fit those into your model, and was there a reason why you went with solar instead of wind for your comparison?
You can certainly have the same graph for wind, that there's nothing special about solar, and the wind has a little bit of lower learning rate compared to solar, I would say, if I'm not wrong. But we basically, with the sensitivity analysis that we had with uncertainty, we just used the wide spectrum of all learning rates in our model. So that basically takes care of all of that. But that's a very good point in terms of like contacting and different technologies. Like I don't know about the company. I have heard them and I read a little bit about them, but I don't know how far from commercialization they are. And that's definitely a promising technology. But one interesting point that I wanted to bring up, and you mentioned that, is basically blowing air, having fans versus a passive capture. Here because we are also building our own prototype here on ASU campus, is actually right in front of my office, and ASU is working with a company to build a prototype. But what we think could give you a major leverage is passive air capture, similar to wind. You just expose your sorbent and your contactor to air without blowing air, because the cost of blowing can really be an issue for companies like Climeworks. I read this somewhere, but I'm not again like 100% sure. So don't quote me on that. But I believe they said out of $500 per ton, like around $50, only 10% is for blowing air. So that's not a huge cost. That is true when you're 500. But if you want to get $100, that will be half of your cost. That's a huge cost for you. And how much cheaper can you make your blowers and your fans? Not much. That technology has been around forever. So passive air capture, we believe, is like it has a huge promise to getting cheaper compared to alternative, because both Carbon Engineering and Climeworks, they're using fans, and we believe the cost of fan can really cause issue. But again, passive air capture, you don't get to run your plant all that often. You definitely will be running less often. Whenever the wind is blowing, you will be basically like a wind turbine. And you will have it has its own challenges, but definitely we think it has more potential. Hope I answered your question.
Yep, great, thank you.
So Habib, we're at time, and I think we could easily, I could talk to you for another 2 hours straight about some questions I have about what's come up just from this conversation. There's a channel, which I'm not sure if you have access to it yet, so I'm going to give you some instructions as soon as we jump off, Habib.
Okay.
That I'd like to continue this conversation in a channel that I just tweaked the name of, that says DACC Research Group under the general category. I think that's a good place to do it. So I'm going to help get you there, and then other folks should be able to see that to ask questions. But it's phenomenal to have someone with you, what you're working on, and your knowledge that's inside our server here. And we look forward to having you involved in picking your brain. One thing I want to point out to you too is I'm not sure if you have access to the R&D channels that we have, Habib. I'll help you with that too. But one of the kind of founding R&D projects that we're doing here at OpenAir is called Violet, and it's a moisture swing miniaturized direct air capture unit that descends from Klaus's research via Tao Wang, who you probably know about at the University of Zhejiang. And so we're looking at the most modular of possible units with that. So we'd love to make sure that you understand that, as well as our other project called Cyan, which Dal has been initiating, which is even a smaller modular kind of micro mineralization device. So I'm going to give you a little bit of a tour of our server here, but I think there's many points of interest based on what you are working on that you might find of interest here and might want to contribute to in OpenAir.
Would be happy. Yeah, definitely.
Great. Thank you so much, Habib. This was fantastic. Really so happy again to have you in the community.
Of course. I hope the presentation didn't overwhelm. It wasn't too much. It was like very compact, a lot of information. I hope that wasn't too much.
It was great. We keep talking. So let's keep the conversation going. Okay. Definitely. Thanks, everyone. See ya.
Bye.